Rafael Vazquez from University of Sevilla. That is going to tell us something about the backstepping. More precisely, he's going to speak with the title Backstepping for PDEs, Fundamentals and Some Recent Results. So thank you very much for accepting to participate in this web seminar, and it's your turn now.
Okay, thank you very much. I would like to start by expressing my gratitude for the invitation to this online seminar. Is it going to be recorded? I didn't ask before, or not?
Yes.
Okay, excellent. Well, I will start, well, first of all, giving some credit. Many of the things I'm going to present today are works in collaboration with my former advisor, Professor Miroslav Krstic from UCSD, Frogan Di Meglio, Long Wu, Gustavo Andrade, Jin Zang, Wang-Wei Chen, and many others that I will credit, and if I forget them, I'm really sorry. I still love you. The way I'm going to present, I will start with something very basic, with the idea of giving you an understanding of how backstepping works. So I'm sorry if you already know this, but hopefully it will be helpful for people who don't know about the method. Okay, so backstepping was was created for ODEs, and it's a very powerful approach that it is also used for nonlinear control of ODEs for systems with a certain structure. For PDEs, it's not exactly the same. It's not so far with a very few sections have not been used for nonlinear PDEs. It's a constructive method that's very characteristic, that it's constructive. And you can use it to achieve Lyapunov stabilization. And the key is that you transform the system into what is called a target system, which has the properties that you really want to have. And in this way, you will somehow shift the eigenvalues in a favorable direction. And the control gains, you can get them explicitly, and you can get them numerically, depending on the problem. Some problems you can get explicit solutions. Some other problems you need to compute them, of course. And I will say sometimes, because I will show to you some problems that I still don't know how to address with backstepping at the end of the presentation. Okay, so the idea is, first you try to identify what you don't want on your PDE. Then you choose a target system in which you eliminate these undesirable terms, if you can. You pose a transformation to go from the original system to the target system. Typically, it will be a kind of Volterra operator, which is always identity minus Volterra, which is typically invertible in most cases, which is an advantage. But there have been, in the literature, particularly in recent literature, other possibilities. And you get your control from this transformation. And to find the transformation, you will have to solve what typically is called the kernel equations, which can be more or less difficult depending on the problem. These kernel equations are typically linear PDEs, hyperbolic or parabolic. We will see some instances in which we have parabolic PDEs. And I will say, as compared with other methods, that it requires some effort, because you need to pose something specific for your system. That's something that makes you work a lot. But there is a reward that you get a more or less explicit controller, and the behavior is typically quite. You can get a lot of properties from the closed-loop system. Okay, so this is the outline of my talk. This is a lot, so I will probably skip some slides to be on time. But I want first to give you an overview of the method for the most simple possible example, a 1D parabolic equation, then talk about coupled systems, and I will draw some parallels between these two. Then the extensions to higher dimensions, and then two new applications. One for the Rijke tube, for which we actually have experiments, and then mix hyperbolic parabolic systems. And then if I still have some time, I will talk about some open problems. So let's show to you the method for the most basic case. And remember, identify the bad terms, pose the target system, pose the transformation. You will find some kernel equations that you need to solve. And if you solve them, and the kernels, the transformation is invertible, you get the controller from the kernels. I will exemplify this right now. So let's, if this lambda is sufficiently large, this system is clearly unstable with this reaction term. And this is the bad term that you will really like to eliminate. Okay, so let's do that. And you pose the target system. Now we don't have this term. It is gone. So how do we go from the U system to the W system? Well, we pose the backstepping transformation. And as you see, it's identity minus some operator of U, which takes the form of an integral from 0 to x. This is a Volterra operator. Why do we call a Volterra operator? Because this can be considered as an integral equation for U of the Volterra kind. And just substituting the boundary conditions at x equal to 1, if you make x equal to 1, well, at x equal to 1, this is 0. This is the control. And this will be the integral from 0 to 1 of k of 1y uyt dy, which is exactly what you have here. So you see you get directly your control gain as a feedback from backstepping. So the only remaining task is to find the kernel. So how do you do that? I will skip these steps, but they are in the slides. So if someone doesn't really know them, from the slides you can very quickly get up to speed and understand how they are derived. So let me skip the details and go directly to the kernel equations. These are the kernel equations, and this is actually a hyperbolic equation with two boundary conditions. Sorry, I'm going too fast. It's typically what is called a Gursat equation, but you can also think about it as a Webb equation with an extra term, sometimes called also Klein-Gordon PDEs. And you can think of it with X playing the role of time and Y the role of space. Let me go back to them. So this is the equation. So you can take a look at the domain. The domain is a triangle, which makes sense. Is the domain of the integral, actually. Remember, it was an integral from 0 to X. And if you take a look at the boundary conditions, they are prescribed here and here. And if you take a look at the characteristic directions, they go like this and like this. So we expect this to be well posed, but the way we are going to show it is by showing an explicit solution, in fact, and also a method of solving it, which in this case gives us the explicit solution. And finally, when you solve it, you get the control gain from the value in this boundary. I personally like a lot this geometric view of the equation, because it gives you some insight into which equations can be well posed or not. Okay, so how do we solve it? The idea is to transform it into an integral equation. This is classic from the literature. So you do this transformation. Let me skip the details. And finally, you get these integral equations. And this is easier to analyze. Why? Because you can pose a successive approximation series, and it becomes quite easy to, first of all, show that it has a solution, and secondly, to actually find the explicit solution to this problem. So let's do that. There are several ways to do it. So you will start from 0 and then from there set up this recursive formula. And if you are able to find the limit, then you are done. But this can also be posed in terms of increments, which I think I prefer. So the first term is the non-homogeneous part, and then you have this recursion. And in this case, it's easy to find the pattern that the solution has, and finally find it, and it will be like this. This is very specific for this case in which you have constant lambda. The reaction coefficient is a constant coefficient PDE, but it can be generalized to much more difficult cases. And I will tell you the paper in which this is studied. It's quite old already. It's 16 years old already. And I will cite it at the end of the presentation. Okay, so we get the solution to the integral equation, and you can also identify that it is actually a Bessel function, in particular, a first order modified Bessel function of the first kind. So in the end, this is the kernel. If you undo all the transformation that you did up to this point, you get the kernel, a Bessel function, perfectly well defined. And from there, you can get the control gain, just replacing x with 1. This is actually the control gain, and you see that it increases as lambda increases, which kind of makes sense because the system becomes more and more and more unstable. And you can also see the shape. You have a zero boundary condition at 0, so it makes sense that you don't need to apply much weight to the state around there, and you apply a lot of weight to the state around the middle. It kind of makes sense. Finally, there is a last part that you need to address, which is the invertibility of the transformation. And how do you do that? Well, you pose an inverse, which actually is like solving this as an integral equation for W. And if you do that, you find a relation between the direct and inverse kernels. Well, in this case, sorry, L will be the inverse kernel. The original transformation was something like this. Let me remind you. Okay. So kind of replacing one into the other, you get the equation for the kernel, which is actually yet another integral equation. And you can, using a very simple argument, show that the only condition you need is that k is bounded, and then you get integrable, of course, and then you get that L exists and is also bounded integrable and has good properties. So, well, let me skip this and just putting everything together. Here you have it. We started from here. We went to here using this control law, which was derived using this transformation, which is invertible. And even in this case, you can even find the explicit inverse. Of course, this is not going to be so easy for many other cases. And now I will go forward and show you more advanced examples. So first, let's talk about coupled hyperbolic systems. What I'm going to show you is, in all these cases, is the same again. I mean, how to choose the target system, how to try to look for a transformation, how to try to solve the kernel equations, so you can see the structure behind this, and hopefully you can apply it to whatever system you are interested in studying. So for coupled hyperbolic system, I mean, this is kind of an old result already. I mean, it has been improved by authors such as Longhu, Jean Auriol, and Jean-Michel Cogon. But let me show to you what we did already some time ago, 5-6 years, I don't remember. So consider this a coupled hyperbolic 1D system in which you have, the U states are M, and you have M, B states. And the difference is that the U states have a boundary condition at 0. That's the reason they have a plus here. So they go, you can think about it like going from, this is X from 0 to 1, and this is T. So the characteristics go from 0 to the right. And in the case of V, they go to the left. You have the minus sign, and the boundary condition is posed at the right. And you consider that you control all the B states. I mean, there are better results than this, but this will help to illustrate how backstepping is used. And you consider that these matrices are full, okay? These are couplings between all the states. This in principle can be unstable. How do you stabilize it? Okay, so the idea again is, how do we pose a target system? And in this case, it's far from trivial. So the idea of the target system is to leave the states that go from left to right the same. Also, you leave some terms there which come from the transformation, because the transformation actually does nothing to the first state. And in the case of the second state, what you do is you put something like this. This looks in principle bad, but we will see that the structure of this G is what helps us to save the day. And you apply a transformation on only that state. Okay, first of all, is this stable? Well, I will show to you that the beta system is stable, and if the beta system is stable, then this goes to 0, this goes to 0, and because this integral is from 0 to x, it's also easy to prove that alpha, in that case, is also stable. I mean, this was not so easy to derive, but it solves the problem. So let's look at the structure of G. So the structure of G is lower diagonal. And this is very important because you can get the stability in a recursive way in this equation. First, you get that the first line is stable, and then the state goes to 0, making this term something that doesn't really affect the second one, and so on and so forth. Of course, choosing this target system implies that you will go to 0 rather slowly, and there are better ways to do it, but it doesn't matter. This was the first result, so I wanted to show it to you. Okay, so now if you do that and consider this target system and the transformation I showed to you, you need to find the kernels. So these are the kernel equations, which are now, these are matrix PDEs. Okay, think about these L's and K's as matrices. And you have these boundary conditions. And it looks like too many, in fact, because these are like first order hyperbolic PDEs, and typically they will accept only one boundary conditions. And here I count 3. So how does this work? Well, in fact, actually it's the opposite. We have more boundary conditions, less boundary conditions that we need. We have some kind of non-uniqueness. This was solved later with some other designs, but let me show it to you. So if you develop the equations into scalar terms, you will see that things work differently depending on these indexes, I and j. So in some cases, we have some boundary conditions. Remember, these are all living in a triangle. So we have some boundary conditions here. We also have some boundary conditions below, and this is new. In some cases, we also have boundary conditions here, which is kind of unexpected, but this is actually the non-uniqueness, part. And some of the boundary conditions, actually, you wouldn't be able to have them and have a well-posed kernel equations. And this is the reason why we have that G term in our target system, to absorb these boundary conditions that we don't know what to do with them. Okay, so what we do is we don't impose them. They come from the PDEs, from the kernel PDEs, and whatever the value is, we put it in the target system, and we are done with that. So let me show to you the different cases. So the Lij terms, they are okay. It's not a problem. You have a boundary condition here, and the characteristic line goes in that direction. That's okay. For Kii, not a problem as well. Boundary condition on the bottom, characteristics going this way. Okay. But the interesting things happen for Kij with I less than j. You will see that you have two boundary conditions, actually one on the diagonal and one on the bottom, But in this case, it's okay. Why? Because the direction of the characteristic line is this one. So there is no problem. You can have two boundary conditions. Of course, there will be a potential line of discontinuity. But this is something you can live with. This is not a big issue. And finally, in the other case, you see here the reason we impose some arbitrary terms for non-uniqueness, because we have boundary conditions here, and this is the direction of the characteristic, and this will give us the value of the kernels in this region. But what about here? So you need some conditions here, so you can impose whatever you want, And this way, we were able to solve this this problem, and this transformation works. So the price to pay in this case is that you will get piecewise continuous and differentiable kernels instead of continuous and differentiable. Okay, that's not a big issue. It doesn't affect the stability result, even in higher spaces, as Long Wu proved in a paper that I will cite at the end of the presentation. And I will show to you how this actually is reflected in a very similar system for and very similar results for parabolic equations, which is something that really pleased me when I obtained this, because it was like a parallel between the procedure for hyperbolic and for parabolic systems. So let me move into the next design, which is the case of parabolic systems. So in this case, we have a parabolic equation with full coupling. Okay, here. Another thing is that it's convenient to order the states, the U1, U2, and so on, in order of increasing diffusivity. We will see why in a moment. And now you also have control on all the states. This is something that is a weakness of backstepping. I will talk about this towards the end. Okay, so trying to follow the guidelines of the hyperbolic case, we add some terms to helping stability, but we suppress the coupling, but we add this G term. Remember, this is very similar to what we had in the hyperbolic system. So if we are able to find the transformation to get from the original system to this, then the control law, as before, as in the 1D case, will be found just by replacing x equal to 1, and you will get it as a feedback, which is really nice. Okay, now what happens with the kernel equations? Actually, this problem, I was stuck with it, I don't know, for maybe 10 years. But then the inspiration from the hyperbolic system was the key to solve it. So these are the kernel equations. And the problem is that, again, it seems to be too many boundary conditions. But the G term, as before, helps us to absorb some of the boundary conditions that we don't know how to deal with. Okay, so we leave them on the equations. That's not such a big deal. Why? Because, again, in a recursive way, you will be able to prove stability. Okay, so now what about the rest of the equations? Okay, you can start to derive some boundary conditions that go to 0. So let me skip the details and go a bit fast. And finally, the idea is these were two hyperbolic equations of second order, to write them as two first order, a system of two first order hyperbolic equations. And to do that, you take the K kernels, which were the only ones that we use, and define L in this way. And if you do that, you become, I call this duplication, I mean, just to give it some name, you get double the number of equations, but the key is that the structure is the same as in the hyperbolic result. So I was able to essentially take these kernel equations that were for a parabolic problem and manipulate them in a way that they finally were basically exactly the same as the kernel equations for the hyperbolic case. This was unexpected to me, but I was very happy with this because I was able to now use the previous result and stop right here. I mean, they have the same structure, same boundary conditions, so of course the same result that Longhu proved a few years ago applies. So with this, it can be shown that Backstepping can also address coupled parabolic system. Of course, again, the price to pay will be that we will have some discontinuities, as in the hyperbolic case. But it's not such a big deal. I mean, here you can see, I mean, the structure is exactly the same of the boundary condition, exactly the same. There's only one difference, which is a plus sign here, but that's not a big deal. Actually, it's better to have a plus than a minus. And this method, of course, can be extended to more difficult cases. I have a paper with this in which you have a time space varying coefficients and some convection as well, a convective term in your coupled system. Okay, so these two results were extension to coupled systems. But there was still a weakness that we only have results in 1D. So next I'm going to show you what we have been able to do in higher dimensions. So consider the following problem in which you are on your domain is an n-dimensional ball. You have Laplacian, and then you have, mimicking the 1D case, some reaction coefficient. And if lambda is large, of course, your system will be unstable. And now, just suppose you can control the outside of your ball. This is a strong assumption, I know. I mean, you can do better with other methods, but I mean, for the sake of trying to see how backstepping works, let's do it. Okay, so how can you address this? Well, the first step was to transform the problem, because it's a ball, into ultra spherical coordinates, which are defined for any dimension. It's kind of a complicated expression, but very clear, with a very clear structure. Okay, if you do that, you get an equation in which you have the radial derivative depending on the dimension. And then you have what is called the Laplace-Beltrami operator on the m-1 sphere, which has a recursive definition, as you can see here. Okay, so the idea to be able to apply backstepping to this is, first of all, exploit the periodicity in the angular coordinates by using spherical harmonics. This is a kind of a Fourier series. Then you can apply the backstepping method to each coefficient, and then you reconstruct, well, you solve the backstepping equation, and finally, you reconstruct the feedback law from the spherical harmonic series back into physical space. So, well, here is the development in spherical harmonics. I don't have time to really go into details, but I mean, the only thing you need to know is that it is kind of a Fourier series. Actually, a Fourier series will be the particular case in 2D. If you do that and use the properties of these spherical harmonics are eigenfunctions of the Laplacian, then you get this. This is the important thing. This equation for each harmonic coefficient. And you are able to control, each harmonic coefficient, because you have full control on the surface of the ball. And these are uncoupled, so you can do an independent design. So I went ahead and did that, and the only thing I did was, okay, I mean, this is a replica of the 1D case, just eliminate the bad term. And if you do that, of course, you will be able, well, you need to pose a transformation, and it's obvious how to pose it. And And now you need to find the kernels. And if you do that, the control law for each spherical harmonic will be this, and you will later need to assemble them back into physical space. Okay, these are the kernel equations. They look kind of bad, but actually they can be even explicitly solved for the case of constant lambda. Let me go ahead and just show to you the solution, skipping some step. The solution is here. And again, we get, I mean, this is very, very, very similar, if you remember, to the structure of the kernel for the 1D case, with some additional terms in which you have the radius and the variable of integration that appears in the transformation, rho. Since rho is less than r, this always works. I mean, this is a well-posed function, and this will be the control law for each spherical harmonic. And now, what you do is you try to assemble this back into physical space. And using, I will skip a lot of details. There is a paper I will cite at the end with the details. If you do it, you find something very surprising, which is that the control law is a combination of the kernel that we already knew in the 1D case times a Poisson kernel for the M ball, which is a striking result, at least to me. I didn't expect it. And I wonder if this can be generalized to other shapes besides the M ball. I have tried, but no luck so far. Some extensions that, let me go also a bit fast here because I don't want to spend too much. The question is, what if the lambda is now spatially varying? I mean, things become harder in this case. Let's consider two cases. The sphere is easier actually than the disk. The sphere, you can almost reduce it to the 1D case. And let me also do a very strong assumption, which is that everything is symmetric, so nothing depends on the angles. So I will only consider the coefficient depending on R. Since everything is symmetric, you get actually a 1D equation, but it's kind of a singular equation because this, also for the sphere. And you may think that this is too much of a simplification, but actually I have seen this use for batteries and other applications. So, I mean, it has some uses. Okay, so in this case, let me start with the sphere. The sphere, there is a transformation, which is very easy, which leaves you with the 1D case. So nothing much to do. I mean, you get, again, the 1D result for the sphere. But what about the 2D case? In the case of the 2D case, these are the kernel equations that you will need to solve. And I was stuck here for a very long time. So let me show you a sketch of the proof that these kernel equations actually have a solution. It's kind of a strange proof, but I need to show it to you. I mean, it's, since my audience is mathematicians, I hope you find it interesting, to say the least. Okay, so let's first do some transformation, and then let's go to integral equations. Defining some variables, finally you get this singular integral equation because it has this nasty term here. So how do we solve this? I mean, the successive approximation procedure, in principle, does not seem to work. But actually, I tried it, and in principle, this will be the scheme, and you will need to be able to somehow prove that these J-key terms, which are defined in terms of the previous through these nasty integrals, are bounded and the series converges. So how do you do that? Well, the idea that I had was as follows. Well, first, G0 is very easy to bound. And then I found a structure that helped me to bound these G terms. So the idea is as follows. First, define this function, which is this kind of complex structure that depends on two coefficients. And the property that this function has is that it verifies the following, in which you can see these integrals have the structure of the integral equation that we are trying to address. Okay, how can you use this to bound the g functions? Well, if you try to bound g1, you see that you get kind of the f here, and then you get a bound on g1 depending on f10 and f01. For g2, on f20, f11, f01, f02, and so on and so forth. And you start to get some numbers here. Well, these are powers of 4, which, I mean, no problem. But these numbers, for me, they were starting to get, I was starting to get a bit crazy. So what were these numbers? You see here, again, 2, 2, 1, 5, 5, 3, 1. So what do you do when you find a sequence of numbers such as this? Okay, I just put it on the internet. And actually, there is a web page with the encyclopedia of integer sequences. And I found this was related to something called the Catalan's triangle. Catalan's triangle, let me show it to you, is this one. So yeah, here you can see the 2, 2, 1, the 5, 5, 3, 1. And if I keep moving on the G's, I found these coefficients. I mean, and they start to become crazy. You do it with Mathematica, and you get these numbers. So how can we exploit that this is actually a very well-known series? Okay, I was able to do it mainly using the generating function. I mean, I was able to find a bound on the series based on this, which is the Catalan numbers, and using, let me skip the details, using the generating function of the Catalan numbers, which is defined as this, you can easily, for instance, derive infinite sums such as this one. And I was able to reduce all with more properties of this generating function, all these complicated sums to expressions that involve the generating function. And then it was much easier to finally derive a bound. And here is the bound. I was able to get, first of all, this expression, and finally this one, which actually is not so easy to, so difficult to finally reduce, and find a final bound, which looks like this. And this was kind of surprising to me. I mean, this is not a big deal. So I wonder if there was an easier way of doing it. Maybe I lost, I don't know, month of my life doing this Catalan thing, but I had a lot of fun, so I don't really care. And this is finally the bound for the kernel, and it works. I have used it in simulations. Simulations don't prove anything, but I mean, it works. Okay, so I had to show you that, and let me now show to you two other applications which are hopefully easier, which are the Rijke tube. This is done in collaboration with people in Brazil, in University of Santa Catarina, particularly Gustavo de Andrade, who did experiments and introduced me to this Rijke tube. So what is a Rijke tube? So the Rijke tube is actually a tube, typically made of crystal. You put a heating element. It can be a resistance or something like that. More or less, can be in the middle or in the lower third, but it has to be in domain, okay? In domain. And now you heat it, and what you find out is that the tube starts to produce a noise. It's humming. And the frequency of the noise will depend on the physical characteristics of the tube. This is probably the simplest possible example of a thermoacoustic instability. It's the same that you will find in combustion engines. And our idea was to do two things. One of them was control the instability in the sense that we will stop the noise. And you can do that because this is a pressure instability. You can do that with a speaker, and also to estimate pressure and density in the interior of the tube, and you could do that with measurements of density, which you can do with a microphone. So you put a microphone at the top of the domain, and you try to estimate what is going on inside while this thing is oscillating. Okay, so I'm going to show you how we solve the second problem, the estimation problem, to show you also an estimation problem and not only control problems. So, well, this is what you can measure with the microphone, and this is what is going on with the pressure. Okay, so let's try to estimate it. And my point is that, I mean, this is like a toy model, but this kind of stabilities can be found in much more difficult problems. Okay. The only thing is that you don't have combustion in the Rijke tube. You just have a resistance. So things become much easier. So the basic model will be using the Euler's equations plus some model for the heat release element, the resistance that is inside the domain, which may look like this. And because you have that point element, you will have a delta function. It's kind of like a point actuation of this heat release element. Okay, and the boundary conditions may contain some control and then some reflection at the upper part. The control we're not going to care about in this presentation. Okay, now you do some simplification, consider Saxonic conditions, you linearize everything, and finally you get something which is more familiar. You get a 2x2 hyperbolic system with still this heat release, point heat release in the middle of the domain with some boundary conditions. The control is still here. And this ODE that tells you how this behaves. Okay. This is like a schematic view of things. So one of the states is a transport PDE. So it goes from left to right, and the other goes from right to left. And then the heat release is here in the middle of the domain. This is a very nice way to represent the system. Okay, there is a way to get rid of this delta, which is actually to consider R11 and R12, R21, and R22 like separate states, and then actually put the Q through the boundary conditions. And this is easy to show using the method of characteristics. And finally, we get a 4x4 system. You have it here. This is a 4x4 system. It's very easy. They are just transport equations with some transport velocities. And now you see the heat release enters through the boundary conditions of some of them and verifies this ODE. So this is a new schematic way of how the system behaves. Now you have 4 states instead of 2. And these are the couplings with the ODE. So this is the ODE part, and this is the PDE. And this is unstable. I mean, if you don't have control, there is a feedback loop, and things become unstable. And what we want to do is to estimate, make an observer to estimate what is going on inside. How do you do that? Well, typically, you pose an observer, copying the plant, and you add some what is called output injection. What is output injection is the difference between your estimation and what you are measuring. Remember, we are measuring the pressure at the top, which is actually R21 at T0. And these are the boundary conditions. Well, if you have the, this is the observer, what you do is you take the original plan and subtract the observer, and you get the error estimation, which verifies this. And now we use backstepping on this. This is a dual design on the control design. the target system has to be chosen again to be stable. So how do we choose it? Let me show to you in a schematic way. Remember that we have a coupling here and a coupling here. Okay, so with backstepping, the only thing I do is suppress this and suppress this. And with this, you are done. Why? Because you have here a zero boundary conditions. This will become zero. Then this is the only term that enters into the ODE. This is unstable ODE, so it will go to zero. You will get 0, 0, 0, and finally the ODE will be 0. I mean, as time goes to infinity. So stability is very easy to prove. And now the structure of the transformation is kind of interesting. Only one state has a Volterra type integral, and the other have full integrals. But this is the important one because it will give you invertibility. And the kernel equations are like this. You have 3 kernels, which are PDEs, and 1 kernel which only verifies an ODE. And I mean, I don't have time to go into details, but you can show again that these equations are solvable. And in this case, they are explicitly solvable. It is quite interesting because you can solve them explicitly, but depending on where the heat element is, you will get, and the parameters of the system, you will get a discontinuous, piecewise continuous solution. And the number of pieces will depend on the parameters of the system. You get a recursive ODE that you can solve, and you can get all the pieces. Let me show to you some solutions of the kernels. Here they are, and you can see how there is, in this case, this is continuity, but it can be more complex. It depends on the relations between the lambdas, which contain all the parameters of the system. It's kind of interesting in my opinion. And also, we proved this in practice. So this is the setup. Here you can see the Rijke tube that they have in Brazil, in Florianopolis. So the heat element is in the middle of the tube. You see it is a crystal tube. And the sensing element is at the top. This is the measurement from the microphone, and if you apply the observer, after a short time it converges. It's not perfect, of course. Nothing in an experiment you can expect to be perfect, but you see the convergence here. It starts at 0 and then very quickly converges and follows quite well what's going on inside the Rijke tube. So, I mean, I think this was nice to have something that show backstepping working in practice. Okay, let me now go to the final part, which is ongoing work with Wang Chen, which is a Chinese student who is doing a research stay with me. But it is a research stay in the sense that he's still in China because it's not the right time to come to Sevilla. So actually, I have never seen him because we work by email. But anyways, he has been very, very helpful. And we work on this problem. Let me show it to you. Is a mixed hyperbolic parabolic system. There are not so many results about this in the literature. So there is one result from Professor Krstic when this is a pure transport equation. Then I have some results with another student from Miroslav's group with only this integral. And then Emmanuel Buitrand has some other results in similar but not exactly the same system. And due to the different nature of hyperbolic and parabolic systems, this is not so easy to address. So I will show to you what we did. So far we have tried two strategies. So first of all, you can see the couplings here. So the hyperbolic state has in the equation the parabolic in 3 places, here, here, and here. But the hyperbolic state enters the parabolic one only through the boundary. And you have only one control, which makes your life more difficult, which is on the hyperbolic side of things. So the first idea was to put some damping onto the parabolic equation and leave this term on the hyperbolic system. And this works, this is stable if C is large enough. We have a Lyapunov based proof of that. And the transformation is kind of interesting because you need to use two triangular integrals, but they are in different directions. One goes from 1 to x, one from 0 to x, and one full integral. So how do you come up with this? Trial, and then you see it doesn't work, it works. And this is inspiring what was already done. And from the second transformation, you get the control. The kernels verify these equations in different domains. The first equation can be actually solved almost explicitly, depending on the case you are addressing. And this equation is the same that I presented at the beginning of the presentation. And the difficult one is this one. And this is kind of unusual because so far all the kernel equations I have shown to you were hyperbolic. And this is the only kernel equation which is in itself parabolic. You see there is a single derivative here, and the domain is a rectangle. Well, it's not so difficult to address. This is the step function. So you will get some kinks in the solution due to the fact of having some discontinuous coefficients, but that's not such a big deal. And this is the first result I got with one way. And then the second result I got was, okay, I was not satisfied with that because you needed a C very large. So how can we try to eliminate the term that was here? Let me remind you, there was a term here. So can we eliminate it? And we thought it was not possible, or we didn't find a way, but finally we realized it was possible to do it considering the possibility of having a delta function in the kernel equations. And this is not such a big deal. I mean, at the beginning, I thought this would make the kernel equation ill-posed, but again, we have been able to use a scheme to address this presence of a delta function in the parabolic equation. Even though I don't know, I didn't find any standard result, but it was not so difficult to address. I skipped the details also because this is not yet published. It will be submitted to the conference CDC, which is in Austin in December. Hopefully in person, but who knows? Maybe not, probably not. Anyways, I'm almost on time, so let me just talk about the open problems and then finish. Okay. Still, you see one of the weaknesses of the method is that I need a lot of controls. In the ND case, I need the control on the whole surface. In the coupled system, control on a lot of the equations. So can we do it in the underactuated case? We don't know. It is a question of finding the right transformation and the right target system, probably. The robustness properties, in this, some people have done some work, not myself. But this is still an open question in general and very, very difficult to address. The group of Frogan Di Meglio, Jan Auriol, Federico Vibriesca have answered some questions. What about terms that are not especially causal, kind of integrals of this type? So an equation such as this. Some kernel, I don't know. I don't know how to address this with backstepping because you get, you need to use a Fredholm time transformation, not Volterra, which is much more difficult to invert, and the kernel equations become much more involved. And as you see, the reaction diffusion equation in the M-ball is still not totally solved. And just to finish, let me show to you what happens if we have for the disk a lambda which depends on both on the radius and the angle. You can try to pose a transformation to a target system in which you eliminate, you see here, you eliminate the bad term. And But if you do that, you get an ultra hyperbolic equation for the kernel. And most of the results I have read on ultra hyperbolic equations are kind of negative. And in addition, one of the boundary conditions contains a delta function. And this looks hopeless. But let me remind you that I was actually able to solve it for constant lambda. And this delta function actually came from the Poisson kernel. You remember about the solution that I showed to you. Okay, so thank you. I think I know it was a lot of stuff, but I wanted to give you an overview of many things that have been going on with backstepping and trying to give you the main ingredients. And here are the references in case you want to read on the details. Many references, and thank you very much. And some advertisement before finishing. There is a parallel seminar actually, and I have to admit, I started to attend this seminar when it was only in Spanish, and I like a lot the idea, so I propose to my colleagues. And I mean, it is kind of similar. It's also done on Zoom, but on Tuesdays, and we are short on speakers. So the audience is a bit more applied, probably. So if you want to give a presentation, we will be more than happy for you to come. And here are the coordinates. Just send me an email, and you can check the website here. So thank you very much.
Thank you very much for this very interesting talk. And now we have some time for questions or comments. So you can ask a question. If you prefer, you can also use the chat to write it. Is there any question?
Yes, I have one question. Hello, Rafael, and nice to see you.
Hello, how are you?
Fine. So this is about the robustness in the case of hyperbolic equation. What happens if you do errors on the speed of propagation? Is it a problem, or you see you have some feedback, but it's computed for some speed of propagation, but unfortunately it's not the good one, but you use this feedback with the true speed of propagation. Is it a problem or not?
I mean, that's an excellent question. I'm trying to think. I mean, if you try to address it from the point of view of backstepping, what will happen is that you will have some extra terms. And I think we could apply similar ideas to what actually we did on our Cyan paper to try to, if the error is small, to try to bound those terms. But I haven't tried, so I'm not totally sure. But I think that would be the idea, to try to, you apply the real transformation, and you leave the transformation that will be the good one. But because you are not actually using the control for the good one, you will have some extra terms. And these extra terms, you will need to bound them, trying to use the stability that you have, and hopefully it will work. But I mean, it will be an interesting thing to explore for sure.
Okay, thank you very much. Very nice talk.
Thank you.
Thank you. Any other question?
Well, if I may.
Of course.
Yeah, so thank you, Rafael, for this very nice talk. I wanted to ask about the control of underactuated parabolic systems. So
okay,
I guess
very interesting
that,
topic.
In this case, if you want to get stabilization results, you should probably assume that the coupling matrix enjoys some particular properties, right? Would you expect?
You mean here, right?
Yes.
Well, I have tried, but without any success so far. I mean, if you have a cascade system, maybe then there is some hope. But I mean, I have tried, and I will be very happy if I get some help on doing it.
Okay, but so probably you need some coupling conditions.
Yeah, you will need some
right?
conditions. You will need some
And
conditions
so
for sure.
then you are expecting to be able to catch these in the construction of the backstepping kernel. Is it what you are trying to do?
I mean, I tried to do it, but the problem is if you don't have control of one of the equations, in principle, if you transform it, you cannot realize this transformation, so to speak. So you will have some extra terms in the boundary due to that. I mean, let me explain it to you. It's very easy to see here. If you try to apply naively this transformation, of course, here, because I have control, I get this. But if I don't have control, imagine W1, so I will have W1 of T1 u equal to u of T1, but I don't have control here, so this is 0 minus integral of 0 to 1. So I will have all the terms entering into the boundary, and then I don't know what to do. So somehow we need to modify the target system, or maybe modify the kernel equations, impose the condition that this kernel is 0. If we could impose that condition, then it will work. But I frankly have not been able to do it. I mean, I have tried several ways, and I consider it a weakness. But maybe, I mean, I was not able to do even this. So at some point, I was able to do it. Yeah, I know that for other methods, it's possible. I mean, I'm just trying to do it with backstepping, if I can. If not, I mean.
So yeah, there are some comments in the chat for.
Yeah.
So if you want. But well, thank you, Rafael, for your answer.
Thank you.
There are 2 comments in the chat. No, 3. Okay, first, Victor Hernandez Santa Maria asked, in one of your last systems, can you do things uniformly and 10 epsilon to 0? I mean, the system coupling a transport equation and a parabolic equation. I believe it was that one.
The last one. I haven't tried. Typically, this kind of trying to do that normally doesn't work, and the reason is that these diffusion coefficients appear in places in the. If you take a look at the explicit solutions, you get diverging kernels. So my guess is probably not, but I haven't tried. I will have to think about it. I mean, if we look at the kernel equations, let me look at them. You will get you see here we have a problem. So I don't know. I mean, typically for the parabolic case, you couldn't do that. So my guess is no. I would say no.
So Constantino Noskitsos says that maybe for underactuated parabolic systems, one would need localized control in the part of the domain instead of just boundary one.
Well, that gives me the opportunity to talk about something I didn't have the time, which is that there is a way actually to post backstepping from the inside of the domain, which is to do a transformation, an integral transformation that starts at a point. But that doesn't really solve the problem. But I just wanted to mention that maybe there is a way of doing that. But backstepping in general is not very well. Is not very well. What happens?
In an open set inside the domain.
Oh, in an open set, backstepping, I think is not so well suited to that kind of actuation. I mean, as far as I know. I haven't tried never to do that.
Okay, so Guillaume Olive says, if I may, for parabolic systems, the stabilization problem has been addressed by Badra and Takahashi by different methods, not backstepping.
Yeah. I mean, I agree, and you, Luz, also have some papers. Okay, I agree. I mean, I don't say that I'm solving problems that no one has solved before. I mean, I know some problems maybe, but some others have been already solved with other techniques. However, what is a possible advantage of backstepping? For instance, people have done designs, adaptive control designs, in which you have some parameters of the system that can change with time. And for that, you can adapt backstepping and try to address these problems, which will be new problems in this case. I don't know. Of course, I agree that I'm not here inventing the wheel. I mean, the wheel has been invented before in many of the cases. It's just a different method.
Okay.
Okay. Very well. Is there any other question, any other comment? Otherwise, we are going to
No, there
finish.
is Christoph.
Is there something? Okay.
So you don't read the chat, Enrique.
Yes, I was reading. I was.
Okay.
It was appearing at the same time I was speaking. Yes.
Okay. So Christoph
Come on.
Zang says, a little comment for internal actuation. There are some backstepping-like methods that work. Among others, hyperbolic systems, dispersive equations. So
I will be very, very happy if you can send to me these references. I'll be more than happy to take a look at them.
Oh, yeah, I'll have a look. And yeah, I'm actually giving a talk next week, and it might be about those applications. So
okay, then
also, yeah. But and thanks for the talk. It was really interesting to get that other perspective for boundary actuation.
Thank you.
Okay. This time I think it's all. So thank you very much again to everybody, and thank you very much to Rafa. It's been a real pleasure to have you here. And we note that there is another seminar, and it is on Tuesdays. So in fact, this is one of the reasons we changed the day of the seminar, in order to make people attend if they want both seminars. And so we're going to finish, and we hope to see you again